The I-beam is an engineering accomplishment deriving its shape from an analysis of the stresses involved in its use. It is designed so that the greater proportion of the area of cross-section is concentrated as far as possible from the center of gravity. The shape adapted itself to ease of rolling, and under test, it was found that even the fillets, an aid in the rolling process, helped convey the stresses from one section to another in continuity. Safety factors were adopted to cover possible inconsistencies in the composition of the material of manufacture. Large-scale machinery and equipment needed in its fabrication lead to standardization. The combination of safety factors and standardization narrowed the practice of engineering to the section of members from handbooks, recommending sections much heavier than calculations would require, and further limited the field of engineering expression, stifling the creation of the more graceful forms which the stress diagrams indicated. For example, the common practice of using an I-beam as a cantilever has no relation to the stress diagram, which shows that the required depth of material from the supporting end outward may decrease appreciably. Joint construction in common practice treats every joint as a hinge, which makes connections to columns and other members complex and ugly. To attain greater strength with economy, a finer expression in the structural solution of the principle of concentrating the area of cross-section away from the center of gravity is the tubular form, since the greater the moment of inertia, the greater the strength. A bar of a certain area of cross-section rolled into a tube of the same area of cross-section would possess a strength enormously greater than the bar. The tubular member is not new, but its wide use has been retarded by technological limitations in the construction of joints. Up until very recently, welding has been outlawed by the building codes. The structural efficiency of rigid connection, in which the shear value and the resisting moment is at least equal to the values of the supporting member, is obtained by the welding of such connections. The column becomes part of the beam and takes on added duties, not usually calculated for columns. The engineer and architect must then go back to basic principles, must keep with and consult the scientist for new knowledge, redevelop his judgment of the behavior of structures, and acquire a new sense, if form derived from design rather than pieced together parts of convenient fabrication. Riveted I-beam plate and angle construction is complex and graceless. Welding has opened the doors to vast accomplishments in pure engineering, which allows forms of greater strength and efficiency to be used. The choice of structural forms are limitless for given problems, and therefore the aesthetic philosophy of the individual can be satisfied by his particular composition of plates, angles, and tubular forms, accomplishing the same answer to the challenge of the forces of gravity and wind. It is now the molecular composition of the metal observed and tested by the scientist through spectroscopy or by photoelastic recordings. His findings may go to the architect and engineer in the more elemental form of the formula, but by that means it shall have become an instrumental part of the builder's palette to be used without prejudice or fear. That is the modern way.